Hello and welcome to this new video, which is about the resolution of linear systems. And what I want to show you is how to resolve a linear system by using the Gauss algorithm and by transforming the linear system you start with in an upper triangular linear system, which is much easier to resolve than the previous one, than the one you started with. So let me show you this by means of an example. So I take the linear system x plus y plus z equal 1 minus x plus y minus 2z equals 0 and 2x minus 3y plus z equals 2. So this is our linear system. So you see it's a linear system of three equations in three variables, and we want to transform it into an upper triangular linear system. So the aim is to solve this linear system by transforming it into an equivalent one. And this means having the same solutions, an equivalent one of upper triangular form. And as you might remember, this transforming into an equivalent linear system may be done by using three operations, which are the following. The first one is that we may take the sum of two rows. We may, as a second operation, we may multiply a row by a scalar which has to be different than 0. And the third operation is that you may switch. You may switch two rows, or equivalently, or even if a less equivalent way, but still you can do this, you may switch two columns. So let me show you how this is done. And the first point is that one produces out of this linear system a matrix, which is a matrix which only remembers about the coefficients of the variables and of the right-hand side. So in particular, on the first column, you put the coefficients of x, which are 1, minus 1, and 2. The second column, you put the coefficients of y, which are 1, 1, and minus 3. On the third column, you put the coefficients of z, which are 1, minus 2, and 1. And the last column is the right-hand side of the linear system. So as you see, this matrix is not an upper triangular matrix, because here you have these numbers here, which are as follows. Okay, these three numbers here are not 0, and they should be 0 if the matrix was upper triangular. And so now we want to transform this matrix by using the three operations above into an upper triangular matrix. And in particular, what we may do is that we may sum to the second row the first one, and we may subtract to the third row twice the first one. The reason why we do this choice here is because of this 1 here, which may be used to erase the minus 1 and the 2 which lie below it. So let me show you what we get in this way. We get a matrix which has the same first row as the previous one. The second row is now minus 1 plus 1, which is 0, 1 plus 1, which is 2, minus 2 plus 1, which is minus 1, and 0 plus 1, which is 1. And for the last one, you have 2 minus 2, which is 0, minus 3 minus 2, which is minus 5, 1 minus 2, which is minus 1, and 2 minus 2, which is 0. Now, again, this one is not an upper triangular matrix because of this minus 5. And so we know what we do is that we use the 2 here in order to erase the minus 1 which lie below it. And in particular, what we may do is that we may multiply the last row by 2, and we may add to it 5 times the first row. And what we get in this way is a matrix which is as follows. So the first row is 1, 1, 1, 1, again exactly as before. Here you have 2, 0, 2, minus 1, 1, which is exactly the second row as before, and now the last row becomes 0. Minus 5 times 2 is minus 10, plus 10, it gives you a 0, and then you have minus 2 minus 5, which is minus 7. And here you have a 5. And now, as you see, this linear system here is now upper triangular. And as you see, the matrix you have is clearly an upper triangle. So what is the linear system corresponding to this matrix? Well, the linear system is x plus y plus z equal 1, 2y minus z equal 1, minus 7z equal 5. This linear system is equivalent to the one we started with, so it has the same solutions, but this one is much easier to resolve. And the reason for this is that, let me now concentrate on this linear system here, is that from the last equation you see that z is minus 5 over 7, simply by dividing by 7 both members of the equations. And now you may use this z to and put it in the previous two equations. So what we get is that x plus y minus 5 over 7 equals 1, 2y plus 5 over 7 equals 1, and z is minus 5 over 7. And so you do the calculations, and then you see that x plus y is 12 over 7, that y is 1 over 7, and that z is minus 5 over 7. And now, as y is 1 over 7, you may replace it in the first equation. And what you see is that now x plus 1 over 7 is 12 over 7, y is 1 over 7, and z is minus 5 over 7. And so, in conclusion, you get that x is 11 over 7, y is 1 over 7, and z is minus 5 over 7. So we may draw as a conclusion the linear system has a unique solution which is exactly the triple 11 over 7, 1 over 7, minus 5 over 7. And this completes the solution of the linear system.